I will show you an example. This is 3D seismic data from Cara C. On the left side, you see the real 3D seismic data after pre-processing, and on the right, you see the model that was got using this data and common image point tomography that allows to get high quality model. And in this model, we do the migration, and here you see the migration results. So you see the layers, and there are subsurface layers, and on the right side one can observe the fault. And finally, the results of the comparison, we compare our procedure with the Kirchhoff type of migration, industrial version, and we see that computationally, we at the same resources, we have got similar computational times. But if you look at the quality, and if you look at this picture, so at the middle, you see the beam migration results, and at the bottom, you see the Kirchhoff migration results. And the beam migration results, they provide better image in some areas where you see here the continuous reflectors, while here you almost don't see it. It was disturbed. And here we've got better resolution. So we've got several layers instead of just one layer here. And so finally, come to conclusions. So we provide the parallel implementation of the 3D seismic beam imaging algorithm that can be applied to irregular data, either in source receiver or in point offset domain, in isotropic and anisotropic media. And the implementation utilizes MPI and OMP technologies, providing two-level parallelization, and the computational time comparison of the developed beam imaging and industrial Kirchhoff migration saw similar behavior, but the real data result proves that developed algorithm advantage. So the obtained stacked images are cleaner and more coherent in comparison with the results of Kirchhoff migration. Thank you for your attention, and this work is funded by the Russian Foundation of Basic Research. Thank you for your attention, and if you have questions, I will answer.
Thank you for this very interesting presentation. So we have time for questions. So I have just a curiosity. So you use OpenMP and MPI to parallelize the computation. Did you try to use CUDA, so using graphic card to speed up the computation? Did you think about?
So yeah, I've got your question. So we didn't use it, and here the problem is that you have manipulation with the data, and it's not like only so when you use CUDA, you effectively you can parallelize the matrix vector operations, but here we come to the operations when we use when we have to manipulate with the big volume of the data, and so in our opinion, in my opinion, so this type of algorithm, it's not really will not provide a big profit at the GPU. So another type of migration where we for example, RTM migration, where we do the so-called raw computations. So it can be very effectively parallelized on the GPU. Right, you're right. But this type of ray tracing type of migrations, they don't have such. They can provide such profit.
Okay, thank you, thank you. Okay, thanks again. Just a virtual applause for your presentation. And so we can go on with the session. We have next speaker, which is Saroya Kanki. We talk about localization in wireless sensor networks using MDS with internode angle estimation. So please.
Thank you. I hope you can hear me.
Yes.
Okay. Just 1 second. I'm having some. Having a little bit of difficulty opening the slides, so it'll be a second. Can you see the slides now?
Yes.
Okay, very good. Thank you. Thank you for waiting. I am Saroja Kanchi, and I'm at Kettering University at Flint, Michigan, in the US. It's about 3 a.m. now, and I'll be talking about localization of wireless sensor networks using MDS, which is multidimensional scaling with internode angle estimation. So I'll first introduce the concept of wireless sensor networks and give a quick review of localization and localizability concepts. And we'll talk about different deployment assumptions, and then I'll talk about some very basics of multidimensional scaling and the new addition of internode angle estimation that's included in the results for this paper. So just a quick overview, wireless sensor networks are a collection of sensors which are distributed in a field of choice. They could be underwater, it could be a rescue mission, home care, object tracking. So the main job of the sensors, as we know, is to simply study some physical phenomena and then gather the information and send it off for computation, and then instigate a change in the environment as a result of the computation. When we have a network of sensors that are deployed in a single mission, we call that a wireless sensor network. And of course, it comes with a collection of protocols and algorithms with some self-organizing capability. The way the sensor hardware is characterized is clearly by very limited computing power, limited storage capacity, and it's equipped with a transceiver to receive and transmit signals within a certain radius, which we call the sensor radius. And we assume that the sensor radius is the same for all the sensors that we're going to deploy in this particular talk. And sometimes there could be lossy transmission as well. So what is localization of wireless sensor networks? It's a problem of once a sensor is deployed in many missions, they tend to move during the mission. So after the initial deployment, we do not know where the sensors are located. So we would like to find the unique geolocation of the sensors so we can go back and rescue them or find them during the mission or after the mission is completed. This localization is performed usually in 2D or 3D, and at this time we'll focus on the 2D localization. Of course, using a GPS will tell us where exactly the sensor is. However, GPS drains out a lot of energy, so equipping every sensor with GPS is not practical. So the way we look at the problem is as a graph problem. We say that the wireless sensor network can be modeled as a network graph in which every vertex is a sensor node and an edge represents a connection between nodes that are within the radio range of each other. And we'll talk more about the edge weights and how they're calculated. Edge weights are what we call the range measurement between the sensors. So obviously the localization problem then translates into a graph problem where we say that given the edge weights that represents Euclidean distance between the vertices, we need to find a unique location for the coordinates of the vertices of V such that the edge weight equals Euclidean distance between the two localization points that we found. So obviously the question then arises saying, given a wireless sensor network as a network graph with edge weights, is it really localizable? That is there a unique location? Is it possible to map it to a unique location on a 2D plane? The answer turns out to be based on graph theoretic property called global rigidity, which has been well known for many, many years now. And it was studied long time ago under the graph theory area. And what happens is that it's proved that any WSN is localizable if and only if the underlying graph is globally rigid. So briefly talking about what global rigidity is, so if a network is not rigid, then it looks like the leftmost diagram here, where you can map it on the 2D plane multiple ways, maintaining the distance measurements between nodes. Similarly, when it's generically rigid, you have what's called a flip ambiguity, as you can see in the middle diagram. And then on the right, we have a globally rigid graph, which means it has a unique mapping onto the 2D plane. So the first thing then is how do we find, this is an example of a globally rigid graph, a network graph that was created with a certain radius on a 100 by 100 square. So the question is, how do we know if a graph is localizable? We know it's localizable if it is globally rigid. However, global rigidity can be found very quickly, which is in polynomial time algorithm is available. However, even if we know a graph is globally rigid, actually finding the location of the nodes is NP complete, which makes this problem challenging. So we are out to try and find the locations given the distances between the nodes or range measurements. And we'll go over a few terminology before I get started with the MDS and the specific algorithm that I'll be talking about. We call some of the sensors as anchors if they are equipped with GPS or if they do not move once it's deployed during the algorithm. Range is a word that we use to measure the distance between sensors, and it can be done by multiple ways, by received signal strength indicator, using time of arrival of the signal or time difference of arrival of the signal. And in deployment of these missions of sensors into missions, there are multiple approaches possible. It could be completely anchor-free deployment or anchor-based deployment where few of the nodes are anchors. It could be range-free or range-based deployment where we know the distance between adjacent nodes that are within the sensor radius. If we do not know that distance, it's called range-free deployment. We could know the angle of arrival between sensor nodes, or we may not be given the angle of arrival. Nodes may be stationary during the algorithm, or they may move during the algorithm. They may be assisted by other robotic deployments, or they may not be. The range measurements, if it's range-based, could be noisy or noiseless. We could be talking about indoor localization with obstructions, or it could be underwater localization. So several deployments are possible of these sensor networks. And there are many, many techniques that have been tried, and I'm going to point out just a few before I get into MDS. The type of approach of the algorithm could be centralized or distributed, sequential or global. Sequential simply starts at one location and keeps spreading the localization across the network. Sparse or dense network could be worked on with different types of algorithms. Some of the very popular techniques have been trilateration and multilateration and multidimensional scaling. And today we look at multidimensional scaling and a variation of that. Or it could be looked at as an optimization problem, or it could even be looked recently, machine learning approaches have been tried for this problem. So just quickly going over MDS. MDS was originally created to view dissimilarity of data that was given in higher dimensions, to view it in either 2D or 3D. What's given is a proximity matrix between pairs of nodes. And the classical MDS finds the location Li, location vector L in 2D such that the distance between the locations Li and Lj equals a function of the proximity matrix where F is a linear transformation. So that looks very similar to what we would like to do with localization, and that's why we applied to localization. And the way the MDS, classical MDS is solved by is is called singular value decomposition, which uses a double-centered square matrix, and it tries to decompose that into u prime, and then u square root of v then gives us the location matrix. And so how do we apply the classical MDS to localization is simply by trying to create a dissimilarity matrix using our range information that we have available between the sensor nodes. However, in a normal MDS, we need all the entire matrix to be filled in, but in our network graph, which is WSN, we do not have all the distances available. We only have the distances between few of the nodes that are within the radio range, if it's a range-based algorithm. So generally, many of the approaches have been to find some sort of a filler, to find the filler between for the unknown distances, and shortest distance is often used. And in this particular variation that we presented, we are trying to find the shortest distance by estimating even the angle between the two nodes. So we use an estimation for the angle, and so we can actually improve. Earlier, shortest distances were way off from the actual distance between nodes, because when the path gets long, the shortest path gets longer and longer, we are going beyond even the network range of the entire deployment area. So because of the error, once there is error in that proximity graph, obviously proximity matrix, obviously the error translates into localization as well when we use MDS. So using this distance angle estimate here that we have estimated depending on the number of neighbors the node has, we're able to improve the way we actually find the shortest distance between nodes. And using this new technique, the results were very good. Here is just a sample network graph with 200 nodes. With the one side is a sparse network with just radius of 12. The other one is 18 with the radius of 18, 100 by 100 units square. And here are the results. For sparse graph as well as dense graph, you can see the red line, which is the normal classical MDS used without the internode angle estimation, and the blue line, which shows a much lower error in all cases for both dense and the sparse graph. Similarly, with a more denser graph with 400 nodes, in fact, the angle estimation works so much better than the regular MDS. MDS error seems to go higher when you have increased number of nodes because of the estimation of the distance gets even more away when you have a denser graph. In a range-free deployment, then we use the actual distance as the radius itself, and then we can still see that the performance of the MDS with the interangle estimation is better in general. Finally, we try to include noise in our measurement, in the range measurement, and we can see that the noise was up to 5%, Gaussian noise was added, and we can still see that the noise in the range measurement included, the performance is still much better than the traditional MDS. And so the future work would be to investigate further into how the angle estimates can be done even more than what has been estimated here. There could be other information that could be used to estimate angles without being given the angle of incidence. And thank you for listening, and I'll take questions now.
Thanks for the presentation. We have time for one very quick question. So if no one has questions, I have a curiosity. So in your examples, you have networks that have 200 nodes. Maybe I missed it, but you tried with very large networks?
Yes. Interesting. Yes. So this is what happens when the network gets very large. We have a very highly dense network. So when we have dense network, there have been already a lot of localization algorithms that perform pretty well on dense networks. Therefore, we try to focus on the sparse network. Sparse network is the current challenge for localization when we don't have enough known distances. With dense network, we seem to know more distances, and therefore localization for dense networks is a much easier problem today.
Okay.
So that's why we don't increase the nodes more beyond. There is a ratio that we use between the number of nodes versus the radius of the network. We would like to keep the radius at a certain level the graph.
Okay, thank you. Thank you again for the nice presentation. So we can go on. We are perfect. Okay, we are perfectly on time. So next talk is about the domination and independent domination problem in supergrid graphs. Uh, and is a work by Ro Wei Yung, Ming Jung Q, and Zhongxin Chen. So I don't know which one is the speaker today.
It's me. It's Mingyong Cho.
Okay, perfect. So
Uh,
the floor is
okay.
yours, please.
Okay. Can you see my
Yes,
screen,
yes, we
my
can
PPT?
hear you and we
Okay.
can see you.
Okay. Hi, every attendees. I'm Cho Mingyong. I'm so great that you can join my presentation. My topic is the domination and the independent domination problems on the supergrid graph. And this is my contents. At the beginning, what is greedy graph and what is supergrid graph? A vertex in greedy graph connected to the neighbor horizontally and vertically. In the supergrid graph, the vertex can connect diagonally. Then, what is about the domination problem? The domination problem is to find the domination numbers,
Sorry, we
which
are stuck on the first slide. We
at first, so, oh
okay,
wow,
okay,
uh, wait, let me change it. What's about now?
okay. Maybe if you okay, yeah,
Okay,
yep,
okay. Oh, uh,
good.
let's okay. Let's talk about the grid graph. And the grid graph is a vertex in the grid graph connected to the neighbor horizontally and vertically. And in the supergrid graph, the vertex can also connect diagonally. And about the domination problems, we need to find the domination numbers, which is the size of the minimum domination set. The dominating vertex can dominate his neighbor. This is the example about the domination set. The red vertex is the domination set. And about the independent domination problems. It's based on domination problems at the condition that every dominated vertex must be independent. It means each dominating vertex cannot be neighbored. Our results are first, proof dominating and independent dominating problems on supergrid graph are NP-complete. Second, we compute gamma rectangular n by the n equal to the gamma independent rectangular n by the n is equal to float n divided by 3 times float n divided by 3. Gamma means domination numbers. Gamma independent means independent domination numbers. This is unknown result. We know that domination problems on grid graph is NP-complete, and hermiation problems on supergrid graph is NP-complete. Then, how we can prove the domination and independent domination problems on supergrid graph? Uh, Assume we have a grid graph. We enlarge each edge 7 times. Then we will get a bigger grid graph. Then we use snake paths from U to the V to replacing each edge of the grid graph. Then we will get a super grid graph like this. How to avoid overlapping when replacing? We use a way called snake path location. A horizontal line is a repeat pattern from up to down. A vertical line we repeat pattern from right to the left. Use this way can avoid overlapping. Let's talk about the minimum dominating set of the snake path. We need to find out the size of the minimum dominating set of the snake path. It has a four situation about U and V. First, we consider U and V both dominated vertex. Then, from W1 to W6, the size of the minimum domination set is 2. It will have 2 domination vertex. The second situation, only U or V is dominating vertex. They will have 2 dominating vertex in the snake path. The third situation, both U and V are dominated, but the dominating vertex are not in the snake path. So they still have 2 dominating vertex in the snake path. The final situation, both U and V are dominated by another dominating vertex, and one of the dominating vertex is in the snake path. They will have 3 dominated vertex in the snake path. We can get a theorem. That is, whatever U and V is or not be dominated or dominating vertex, the minimum dominating set is the 2 dominating vertex in the snake path. We use this theorem to provide dominating problems in the supergrid graph is NP-complete. This is a theorem. A gridded graph has a dominating set D with the size less or equal to k. If and only if a supergridded graph contains a dominating set D hat with the size less or equal to k plus 2 times edge of gridded graph. Assume we have a gridded graph with the dominating set D. The size of D less or equal to k. Then we use the way we have do it before to turn gridded graph to become a supergridded graph. With the domination set D hat, the size of D hat less or equal to k plus 2 times the number of edges of the gridded graph. Then we have another supergridded graph. Assume we have a supergridded graph, we can turn it to be a gridded graph. A supergridded graph with the dominating set D hat. The size of D hat small or equal to the k plus 2 times edge of gridded graph. We use the straight line to replacing each edge of the supergridded graph. Then we will get a big gridded graph. Then we striking 7 times. Then we will get a gridded graph. With the domination set D, the size of the D equal or smaller than k. From theorem, the dominating problems on the gridded graph is NP-complete. To resolve to corollary, the independent dominating problems on supergridded graphs is NP-complete. This part we are talking about the dominating numbers of the rectangular supergridded graph. This is a rectangular supergridded graph n by the n. Okay. In this part, we need to compute gamma rectangular n by the n equals to the gamma independent rectangular n by the n equals to the float n divided by 3 times float n divided by 3. First, gamma rectangular 2 by the n is equal to the float n divided by 3. Why? Let's think about a 6 point is a group, and a group has a leader. It's called domination vertex. We can make rectangular 2 by the n in many parts of the group. So gamma rectangular 2 by the n equals to the float n divided by 3. In the same way, we can get a gamma rectangular 3 by the n is equals to the float n by the 3. Now we think about a group is a 9 point, and every group has a dominating vertex. And what about the gamma rectangular n by the n? We use the same way to do it. We use this line to make n by the n to many parts of the rectangular 3 by the n. So gamma rectangular by the n is equals to float n divided by 3 times float n divided by 3. What about independent domination numbers of the rectangular supergrid graph? There is a theorem. A graph contains any graph from 1 to the 16, h1 to the h16. The gamma g will equals to the gamma independent g. And the rectangular supergrid graph contains h3. So gamma rectangular n by the n equals to the gamma independence rectangular n by the n equals to the float n divided by 3 times n divided by 3. The conclusion: we prove that domination and independent domination problems on general supergrid graph are NP-complete. And then we provide a formula proof to compute the minimum dominating set of a rectangular supergrid graph. In addition, we used a simple math to verify the minimum dominating set of a rectangular supergrid graph is also a minimum independent dominating set. Thank you for listening. Does anyone have any question?
Thanks for your presentation. So we have time for questions.
So, can you hear me?
Yes.
Yeah, yes.
Okay, I have a question. Like in page number 27, like we know that Rn by n is floor n divided by 3 times floor n divided by 3, right? But how we can know that?
Oh, we can cut a rectangular n by the n in many parts of rectangular 3 by the n. So the most we can get the float n divided by 3 rectangular 3 by the n, and the gamma rectangular 3 by the n equals to the float n divided by 3. So it's let me use it. So we have float n divided by 3 rectangular 3 by the n. So the gamma rectangular 3 by the n is float n divided by 3. So the gamma rectangular n by the n equals to the n divided by 3, m divided by 3 times n divided by 3. Okay.
Okay, thanks.
Any questions?
If you can ask a question, I think, is it true that for general graphs, this problem is NP complete? And then is there an upper bound known for the independent, for the, dominating set size
Uh-huh.
for general graphs?
Yes, for the general graphs.
Is there
Some
a is there
some
upper
special
bound? Yeah, go
uh-huh.
ahead.
Is some special supergrid graph is not use cannot use in this ceremony. Yeah.
Okay, if nobody has other questions, we can move on to the next speaker. Thanks again to the speaker. Okay, next talk is
Okay.
about,
Thanks.
thanks to you, Tower and Security IoT platform with high rate transmission and low energy consumption. Is a work in collaboration, and the speaker is Lam Nguyen. So please.
Yes, my name is Lam Nguyen. Can you hear me?
Yes.
Okay. Screen entirement. Also, why I can say my screen?
We lost the speaker. Okay.
Okay, I will share my screen.
Okay, we can see you. Do you have
Yes.
problems with your connection?
Okay, I'm connection, but I can share my screen. I don't know why. Why? Sorry, when you do this.
Are you able to share your screen?
Oh, I will. Okay. I don't know why I can share my screen. I only share the room, but the presentation is not. Okay. Okay. Can you see my
Okay.
screen?
Okay,
Yes.
yes, yes.
Okay, sorry.
It's okay.
Okay. Good morning, everyone. My name is Lam Nguyen, and I will present my paper with the title toward a security IoT platform with high rate transmission and low energy consumption. My outline will include 6 sections: introduction, related work, IoT platform proposal, implementation, evaluation, and conclusion. We go to part one, introduction. In part one, we will consider some point. IoT technology it become the important technology because it has grown rapidly and applied to many fields. For example, smart city, healthcare, supply chain, industry, and agriculture. According estimate, there will be 5 billion device IoT connects in by 2025. There are many protocols for IoT, but the MQTT protocol is the most
Sorry,
popular because
sorry. We are stuck on the first slide. Okay.
okay, you can
Okay.
see the instruction like
Yes.
okay, okay. There are many MQTT protocol, but MQTT is the most popular because it has high transmission speed and this is why protocol, so it is suitable for the limited device. Besides the benefits, MQTT protocol has many drawbacks. For example, weak security mechanism, and we had to straight up reliability and energy consumption.
好，你可以睡觉了，大半夜把你叫起来，拜拜。
what
小唐啊，
to address this problem, we wrote both IoT platform with able to circumvent really reliable transmission capability as MQTT 02, but still provide a fast transmission rate and low energy as MQTT 0. In addition, IoT platform also improve security mechanism.
OK，
Okay, we go to
林
part
电
two
话，
related. In part two,
拜
we
拜。
summarize some research paper.
发什么呆？小唐在上课，在关麦。
Power incremental UOR to enable access control for MQTT protocol. Benjamin IC UOR and introduce the concept of personal cloud middleware to manage the revision of user and IoT device. Logic Control add-on use Kafka MSQ as a transmission system to transmit a message between MQTT broker and the rest of IoT system. This helps to improve the performance of the system as well as provide easy scalability. So the NAS add-on estimate energy consumption when in many MQTT protocol QoS level. And finally, Ali add-on argued that MQTT QoS2 will be removed from his stack because it has large energy consumption. We go to part 3, design of IoT platform. You can see the figure 1 illustrate our architect of IoT platform. Our architect will be divided into two parts: the system architecture and the software architecture. In architect, will include MQTT ROSI, MQTT broker, which deploy a cluster, single sign-on ROSI, single sign-on server, single sign-on database, and Kafka MSQ. In software architecture, we have 3 parts. The user who use IoT service thing is the physical device or application on the user, and the channel add a logical information for manage where user put this message to thing or the thing and the thing will be supplied the channel to receive message. With software architecture, we build a RON concept that only allow user to send or receive message on his or her thing when those things are mapped to the channel on by the user. You can see figure 2 illustrate the rosette published message. This rosette will follow the step below. User step 1, user or publisher will be sent message to MQTT rosette instead of direct connection to MQTT broker. Each outgoing message has contained all our token, and this token will be authenticated by single sign-on rosette. After authenticate user token, single sign-on rosette will check the user RON. User RON will be involved to the permission. For example, this user is allowed to send or only receive message, or is this user allowed to send message on this channel or not? After checking user validity and RON, this message will be sent to MQTT broker and finally reach the Kafka message queue. Similar, the receiver who attend and check RON by single sign-on rosette will receive the message via MQTT rosette. We go to part 4, implementation. You can see figure 3 illustrate the user organization as model 3. Which this model is suitable for company and organization. In this model, we have 3 definitions. The first one is the root user, the second is the parent user, and final is the child user. Root user play a role as the network, IoT network administration. The parent user can create, delete, or enable, disable child user. The child user will be connected to the parent user via user parent ID attribute. If one user has status is disable, his or her can be interact to the IoT platform. This helps to isolate the group of users or even the organization when the system will attack. We go to part 5 evaluation. In part 5, we have 2 scenario steps, and in the test 1, we will evaluate the message encrypted when using IoT platform or without using IoT platform. You can see the figure 4 illustrate the scenario 1 test. In this test, we use the Wireshark software to capture the message that's transmitted between the thing and the server. If we use the IoT platform, the message will be encrypted. And without IoT platform, the message is as LAN test, and we can easy to read the information. The test result is illustrated in the figure 5. In scenario 2, we will deploy the IoT platform on several servers with the configuration listed in table 1. In scenario 2, we have 3 small steps. The step 1 is the thing connect directly to MQTT broker and publish message SQL2. In test 2, we have the thing connect to MQTT broker through the IoT platform proposal and publish message SQL0. But in this case, we don't apply the security check. And in test 3, the thing connect to MQTT broker via IoT platform, publish message SQL0 and apply the security check function. In this step, we will simulate the concurrent user by using ZMeter software, and then we record a high XCU without the system failure. The test result is illustrated in table 2. And for the test 1, we have the high HCCU is 300. The test 2 and test 3 have the high HCCU is 500. But in test 2, we have high robust because in test 2, we don't apply any security check. The final part is it and its conclusion. In this research, we try to reach some target. First one, through security mechanism of MQTT protocol. Second, we ensure like about transmission as MQTT QS2, but still provide high rate transmission and low consumption at MQTT QS0. The third, our IT platform ensure don't lose message when the connection is broken in comparison with MQTT protocol because this protocol has no buffering mechanism. And final, we increase management ability in user thing and channel. For future research, we will consider about the blockerless architecture to avoid the single failure point, and in comparison with the brokering architect using MQTT broker, and we also consider the decentralized authentication. Okay, thank you.
Thank you. Very nice presentation. We have time for a very quick question. Okay, so no questions. Thanks again. And this is the end of this session. Now we have a break. For those of you who would like to attend the following session, we will be here in a quarter, so at 10:15. So thanks all the speaker of this session again, and see you later. Thank you.
Thank you. Goodbye.
Thank you.
Natalia, abbiamo solo uno degli speaker di questa sessione,
Ok,
che è qua in presenza con me, professor Gervasi.
ok, sì.
Gli altri due, boh.
Vabbè, attendiamo qualche minuto al massimo.
Va bene,
poi.
ok. Tanto abbiamo solo 3 in questa sessione.
Sì, infatti abbiamo un po' di margine di tempo in più.
Esatto, siamo un po' larghi, ok.
Streaming is on. Streaming is on.
Okay. Hello, everyone. We have had a long break since the first speaker of the session didn't show up. So we can go on with the second speaker of the session, which is Professor Osvaldo Gervasi. He will talk about implementing a scalable and elastic computing environment based on cloud containers. So I will share the screen. So, please.
I sit here.
Yeah, go on, yeah.
Okay, hello everyone. The title of I guess
Yeah.
there is something.
We need to move it to this window.
Okay.
Okay.
Presentation. Okay, good. The title of my talk is Implementing a Scalable and Elastic Computing Environment based
Prof,
on...
I don't see the presentation now. I see the browser.
Sorry, what you see?
I don't see the presentation. I see the browser now.
Ah, okay, sorry. What about now?
Okay, okay, now it's going. Okay. Perfect.
Okay. So the title of my talk is Implementing a Scalable and Elastic Computing Environment based on cloud container. The work has been carried out by Damiano Perri, Marco Simonetti, which are my PhD students, and Sergio Tasso, professor at University of Perugia, and Federico Ragni, who is a technician of the same university. The basic idea behind this paper is that we want to afford and to present a solution, a series of best practices, and to implement a very reliable and scalable architecture based on cloud resources. All the stuff is based on open source software. So the idea is that an organization, a company, can afford the new challenges that particularly COVID-19 has made to a lot of scenarios in order to push towards a digital world. So now even companies are demanded to adopt these new strategies in order to afford this type of challenge. And the idea is quite simple because we have all this open source software, and we provide some line guide to assemble the various components. You know that the main issue regarding open source software is that it's not a commercial product, it's not well packaged, so it require usually some competencies, some work behind. But the advantage is that you can do an extraordinary infrastructure essentially without paying fees for licenses or other stuff. The other part is that the time spent to acquire the competencies is well spent because these competencies will be very helpful for the future of the organization. So this design can be suited for companies, public administrations, organization in general. And what we want to stress is that adopting this type of infrastructure, we have several advantages. In particularly, we are able to implement an infrastructure that is able to scale. That means that as soon as the number of users increases, even suddenly, the infrastructure is able to respond in a very efficient way and allowing to distribute this type of services of applications with a variable number of users without wasting time, without delays, or at least significant delays. How many times we have seen portals, services that in front of a massive number of users crashes in a very ridiculous way. Also, at least in Italy, we have several examples in the last couple of years when the expected number of users were of course high, like when the government provide the subsidiary for enterprises. So there were very critical periods. So it was obvious that the number of users will be very massive. And what we observed that the website did not respond in time. So making people confused, even in some case desperate. So let's say this can be easily avoided adopting a similar infrastructure. The other part is that the proposed infrastructure is maintainable and offer as a consequence some very important outcomes. The principle is that the system will be fault tolerant in this approach. That means that even if a damage occur, if an hardware problem occur, if even in some cases another attack occur, the system is able to respond in a very positive way. The other part, the most evident example, always in Italy, was in the Lazio region, where they lost all the data for a week regarding vaccine. So it's a very, very, very dramatic situation. And if you adopt a similar design, you can establish a disaster recovery very easily because you can distribute the server among different areas of the country, and this is only a matter of resources. And you can avoid similar facts because you do not have to recover from a backup and having lost a significant amount of data. You have an instant backup with our design. So the keyword in this presentation is container. Container means that is a very easy and new technology, which is characterized by being a lightweight technology. So that means it's very, very light and easy to maintain, easy to deploy. So we may have a cloud environment behind a data center, and we can run those Docker containers over it, implementing the full service we want to adopt. This is the general structure of a Docker system. We have the client that will use portals or different application programming interface, and so this user will connect to a daemon, to a Docker server, and usually to deploy a relative complex infrastructure, we need several Docker images, containers, because in a container, we manage only one type of application. For example, you know that internet is based on the use of domain name system that convert IP addresses, names and IP addresses. So a DNS server usually run on a Docker instance, only the DNS server. This is very important because reducing the number of stuff that are running inside an instance, you reduce dramatically also the probability of having a crash for several reasons. For example, for a bug in the operating system or a bug in the software itself. So in this case, we have something very, very light, very simple to manage, and very efficient because only run a specific program. So usually we have web servers that access database server that access file system. So all these stuff are managed by different containers. Those containers are kept from images. This is the crucial part. This is probably the most, let's say, delicate part, because it's not like when we use a single server with several programs inside, where all is instantly, let's say, provided, distributed to the clients. In this case, we have to provide images. So a Docker image is something, let's say, static. It's not so dynamic. But in production system, this is the right choice. When you have a web server, a portal that runs a specific task, you need stability. So you access the image that is a consolidated version of the software, and you deploy this type of images. So the containers are kept from those images. There is a registry to map those images, and in this way we deploy our server. Essentially, the way we may adopt to deploy services are the following. We have the very old legacy service delivered through a single server. Okay, you have a computer, you have a server, you install inside a server several applications, several software, several pieces of code, and you run everything inside the server. What is the disadvantage of this architecture? The most important one is that you cannot scale. You have only a server, and you cannot put another server that will reinforce in case of need this design. So it's a static design, may scale only vertically. That means that you can change the server. You may adopt a new server with a more powerful CPUs, more storage, and so on and so forth, but you cannot scale horizontally. Scaling horizontally means that if in this moment I have 10 clients, I can serve them with only one instance. After 1 minute, I have 1,000 clients. I can launch let's say 10, 100 Docker instances, and those clients will be served instantly without any delay, without any loss of service. The other way we can deploy services is the legacy architecture based on virtual machine. This is interesting because, you know, when you adopt a virtual machine, you have several advantages. You can easily make backup because it's only a matter. When a virtual machine is implemented in a server, all the information related to the virtual machine, all data, are in a file. So you can copy this file to make backup. You can move the file to another machine to optimize the usage of the hardware, for example. Imagine a cloud data center. We have, in a given moment, two virtual machines very intensively loaded in a server, and we have another server which is completely unloaded. We can move the virtual machine from one server to the other in order to balance the usage of the computers and provide better services. But it's still more complicated than containers, because the virtual machine is essentially may host several applications, several software again, while the container is much more light because contain few things, so it's much more easy to manage. So the modern architectures are based on containers, and when you talk about containers, you talk about Docker. Docker is an open source software, free and available, so you can use it for free. Those architectures need to run on of course, on a physical infrastructure. The physical infrastructure may be a private cloud. In this case, for example, a public administration may have a data center, its own data center, so a series of computers that will deploy a cloud service, like the commercial one, like the big IT companies presently in the world. So we may have a private cloud that has the same approach of the public cloud, but where the data are kept inside the organization, do not go outside. So, for example, if you have sensitive information like sanitary information about vaccine, about disease and so on, this is recommended because, of course, you keep the full control about your data that do not occur usually on public clouds. The third solution is an hybrid solution. Let's say I may implement a private cloud, so I keep my data locally, but for example, I can use spare CPU resources, so computational resources from a public cloud server. So combining these two aspects, we may deploy the infrastructure we prefer. Of course, I repeat, for a public organization, for people managing sensitive information, the most reliable infrastructure is a private or hybrid cloud and Docker, based on Docker services. Of course, the legacy architecture have several disadvantages, some already presented, but the main is the very difficult maintainability and the lack of fault tolerance, because if the only machine goes down, you lose the service. The scalability, as said, is impossible, and usually you proceed by a backup and restore modalities. So you make backups or your data. If something occurs, there is an hardware problem or a software problem, the machine crashes, you can restore the information from the backup you have already done. But the problem is that you lose the information that has been produced, managed after the last backup. This is the essential problem we have. The architecture based on virtual machine are, as said, several advantages already presented, and the main disadvantages are that there is a significant hardware impact because of the complexity of running the virtual machine. Also because to run a virtual machine, the hardware has to be equipped with enough RAM, random access memory, and also several resources to be able to deploy to run. So this is the scheme regarding these two approaches we have already described. In the legacy architecture, we have the hardware, we have the operating system, we have the several pieces of software running on top of the operating system, okay? In the legacy with virtual machine, we have the hardware, the operating system. It depends on the approach we use for the implementing virtual machine. However, usually we have an hypervisor that will be able to implement the virtual environment. And on top of the hypervisor, we have several virtual machines that can run different services, different software at the same time, optimizing, of course, the usage of the hardware, because you can run contemporarily several virtual machines, so you can deploy from the same machine several services. We mentioned before the disaster recovery because it's a very important issue. All organizations are requested, but since several years by law, to implement disaster recovery. In reality, only a few have already done suitable, let's say, design, suitable organization. Disaster recovery means that if any disaster occurs, that means an hacker attack or a physical, an earthquake or any other event, you are able to restore the information, to manage the information without interruption. This is the ideal design we want to implement. To measure the effectiveness of the disaster recovery implemented, three metrics have been defined. The first one is the service level agreement. This means the percentage on a year where the system is available. So that means that usually we measure SLA about 99%, for example, or 99.90% in order to have the system always on. This is the ideal scenario. The other metric is the recovery time objective, RTO. This is the maximum accepted time between the interruption of the service and the moment the service is restored. So we want an high SLA and a very low RTO. The same for the recovery point objective, the RPO, that measure the maximum acceptable time between the last data backup and the time data loss because of a disaster. So in this case, also in this case, we want the minimum value, possible value. Okay. We may have different implementation of disaster recovery. The first one is, as I said, backup and restore. The pilot light is an implementation where we have a backup physically separated. And in this case, the RPO is of the order of minutes and the RTO of hours. The war standby, we have two backup sites synchronized, possibly in real time. In this case, the RPO is seconds and RTO is minutes. And finally, the most effective solution is active-active. I mean, we have several servers running contemporarily and able to deploy the service to the user. In this case, both numbers are near zero. So we are discussing the high availability architecture. So this is our design. We have two areas possibly separated from a long distance in order to guarantee that in case of disaster we can recover easily the data. The two areas are connected via a virtual private network. Data is copied in the two zone in automatic way, and if a zone will fail for an hardware problem or a physical problem, the other zone take controls and is able to respond immediately. So for this design, the load balancing is crucial. Load balancing means that when the user connects to a service, the request is captured by this software that will distribute among the available resources the request. So it will act in a way that all server will be, let's say, equally loaded during time. And in case of an increase of requests from the user, the load balancing is able to launch new instances of the containers. So instantly is able to react to a large request, providing large resources. And in this case, we are able to scale very easily. There are different policies we can implement. So this is the general scheme. Some consideration has been has to be adopted regarding the database design, because the database is a crucial point for several services and portals. We use MariaDB RDBMS, that is an open source software, which is configured as a master slave. So we have only one master, that is the container that has the role to write, has the permission to write. He can also read, of course, but all write operations to the database are carried out by the master. The other instances are slaves, so they access the database in read mode and are able to respond to the queries, to the request made by the users. So in production, we have one master, several slaves that will increase in number if the user will increase the request. The other delicate point is the distributed file system, because the container do not has itself a disk to write. So we have to implement this disk as a distributed file system. We adopt Blaster file system, which is a network file system, very efficient and still open source. All things I mentioned are all open source. So at this point, the scalable design is implemented, because we may have several Docker instances running and orchestrated by the load balancer that will kill or launch new instances in accord, considering the number of requests that are sent to the server. The maintenance is quite straightforward, because there is a particular language called YML. So there are files that the sysadmin has to write to design, but then everything is automatic, and the infrastructure is completely easily maintained by using those files. The IP address is crucial. So normally, to guarantee the disaster recovery, we need different subnet, different type of IP addresses in order to be connected and guarantee the disaster recovery solution. So in conclusion, this is our work. Want to define a series of best practice of recipes that, using open source software, so free software without license cost, but with, of course, some knowledge regarding how to configure the software, but quite easily we can implement a solution that will reduce the RPO and RTO and guarantee that we can implement a disaster recovery design perfectly horizontally scalable and able to resist to deploy the servers even in presence of hacker attacks or other type of programs. Thank you.
Thanks for the very nice presentation. We have time for questions. Let's see. No questions, so thanks again.
Thank you.
I don't know if we have the next speaker. No, I think didn't show up. Okay, so this is the conclusion of this session. The third part will be at 11:30. The chair will be Alessandro Buccini, and Natale will be the technician also for that session. So see you at 11:30. See you later. Bye. Bye.
Bye.
Okay, so buongiorno, good evening.
Buongiorno. Yes.
Good evening, everybody. Good morning, everybody. So we are now moving to the 11:30 session. So the first contribution is entitled Synchronization Overlap Trade-off for a Model of Spatial Distribution of Species. And the authors are João Bianco, Paola Prata, Fernando Canovas, and Paolo Fazendeiro. So please, I actually don't know who the speaker is, but please, the floor is yours.
I don't see the speakers, Prof.
There is no speaker?
No.
Okay, then we have a 15 minutes break.
Okay.
Okay, then see you in 15.
Streaming is on.
Hi. Okay, so is either Dmitry Nekludov or Maxim Protasov online or in the room?
Yes, I'm here.
Okay, perfect. Okay, so if you want, we can start trying to share your screen.
Yes, I'm trying. So, is it fine?
Perfect. Yes.
Can we start?
We still have a couple of minutes before
Okay.
the time, so we don't want anyone connecting for you just to miss you.
Okay.
I can start introducing you. So you have the full 10 minutes. So the second, which is actually the first talk of this session, is by Dmitry Nekludov, which is a joint work with Maxim Protasov, and it's wave-consistent ray tracing using Chebyshev polynomials representation of a model in three dimensions. So please, the floor is yours.
Okay. Many technical applications require calculating travel times and travel paths between known location of source and receiver of some probing signals. In seismic explorations, such a problem, known as two-point ray tracing, plays a significant role. Modern seismic exploration problems are usually three-dimensional. The spatial size of the computational domain may be huge. This is why I put here the first item. We need fast calculation of ray trajectories and corresponding travel times in 3D medium. Methods oriented for travel times and travel path calculations usually are based on high-frequency approximation of seismic signals. It is so-called ray method. They don't take into account the effects caused by the fact that temporal spectra of real seismic signals are band-limited. High-frequency approximation often leads to the non-physical behavior of the constructed rays and corresponding travel times. This is why I put here the second item. We need to take into account band-limited nature of real seismic signals. So let the initial and final points of the ray are given. So we need to construct the array between source and receiver. By definition, ray is a such trajectory that provides minimum travel time of some signal between source and receiver. It is so-called Fermat principle. Practical experience has shown that the so-called shooting method for solving a two-point ray tracing problem often does not provide satisfactory results. I will present some examples below. For three-dimensional cases, shooting requires significant computational resources. An alternative to the shooting method is so-called bending method. So we have a number of trajectories. So we modify it in some way to provide minimum of some functional, namely travel time. So bending method, it is based on modification of the initial curve that connects source and receiver pair in such a way to minimize the travel time along with trajectory, which is Fermat principle. So we suggest the following 3D model representation. Geological medium is usually represented as a set of subhorizontal layers formed by sedimentary rocks. The most intensive variation of physical properties, such as velocities or density, occur in depth. In depth, it is marked by z-axis. We assume that a 3D model of the medium is represented as a set of layers separated by non-planar surfaces. In each layer, a function of slowness, the value of the reciprocal of seismic velocity is specified. It is marked by S. Slowness in each layer depends on two lateral coordinates, x and y, but does not depend on depth or z. The function s depends on x and y is defined as two-dimensional Chebyshev polynomial of third order. Example of such representation is shown below. And surfaces, two-dimensional surfaces, is also represented by Chebyshev polynomials. So what about ray trajectory parametrization? Having in mind the model parametrization described above, we assume that in each layer, the ray is a straight line segment specified by coordinates of the intersection point 1 and 2, x, y, z1, x, y, z0, for example, with two neighboring surfaces. The ray will be fully defined if appropriate coordinates of intersection point x and y will be defined. We aim to find a proper location of straight line segments to minimize travel time calculated along a trajectory. We call a set of coordinates pair x and y as a ray parameter. So let TG means travel time within one layer. Total travel time from source to receiver point is the sum of travel times along each segment. To construct a ray, a trajectory satisfying Fermat principle, one must minimize the total travel time. It means we need to minimize this functional. Minimization, we need to minimize this functional with respect to intersection point x and y, g. Source and receiver position are fixed. Minimization of the cost function may be performed using any known nonlinear conjugate gradient method, any variants, and so on. To apply any conjugate gradient approach, one needs to provide two functions. One function calculates cost function, travel time, and also we need to calculate gradient. It means derivatives of travel time with respect to intersection point. Having in mind our parameterization, our model parameterization, the travel time...
Галя, здесь я вижу...
Excuse me? I'm sorry?
Sorry, Dmitry, you have a couple of minutes left.
Sorry. Okay, travel time has an analytical expression, so we can run conjugate gradient with no problem. So when I present some realistic numerical example, here we can see rays calculated with standard shooting method, rays calculated by the bandit method. And we can see that this rays looks much more better. Also, we proposed modified Fermat principle, modified Fermat functional. We minimize not only travel time, but also length of array. It provides much better coverage of the arrays. So we are satisfied. Travel times are coincide, which is good, but array distribution using modified functional is much better. And here we can see example of inversion, true model, initial model, and recovered model. So this approach works not only for travel time and travel path calculation, but also for inversion, which is very promising approach. That's all. Thank you.
Thank you for the very nice talk. Do we have any question feel free to unmute yourself, and if you're in the room, then I can relay the question if the speaker is not able to hear you.
Okay, thank you.
Okay. If there is no question, let's thank the speaker again. Oh, I didn't show up. Okay, we're a couple of minutes ahead, so we can already start at least share the screen with Vladimir Cerveda that I see online.
Just a moment, I'm trying to...
Yeah. Okay.
Okay. Sorry. I'm not sure what is happening.
I think you have to reduce the icon the browser.
So let me try to log out and log in.
You don't need to log out. You just move to your PowerPoint presentation and we'll be fine.
Okay.
Perfect.
Okay.
Is it okay?
Yeah.
So I'm ready to start if it's possible. If you suppose that it is fine,
yeah.
I will start. Okay.
We can start. Yeah. So let me introduce you to. So the third and last talk of this session is by Vladimir Cerveda in collaboration with Ekaterina Efimova and Galina Reshetova, and it's entitled "Full Waveform Inversion in Viscoelastic Media." Please, the floor is yours.
Okay. Thank you very much for presentation for introduction. So I'm going to talk about simultaneous recovery of the all five parameters of viscoelastic media. I mean the wave propagation velocity, P and S wave, and also the quality factors for P and S wave also. I should say that there is also the very well-known problem with the density recovery. So in this talk, I'm not going to deal with such kind of problem. I will be concentrated on the coupling between elastic parameters like Vp and P and S wave propagation and P and S wave quality factor. Why it is so important, especially, I mean, it's so important for the North Sea shelf of the Russian Federation. That because of the global warming, there is increase of the temperature of the Arctic shelf, both for the land part of the Arctic shelf and the sea part of the Arctic shelf, and this leads to the melting of the gas hydrate, and so that means that there will happen to be the very high concentration of methane, which is going to act like a very huge blast. For example, explosion, which very huge explosion. For example, there are the well-known craters on the Yamal Peninsula. So you can see it here. It is, I mean this one, with a huge diameter of the almost 100 meters. And the same craters, the Norwegian geophysicists recovered in the Barents Sea. So it is again because of the melting of the gas hydrates due to the global warming. So, but it is, of course, it may be very, very dangerous because in this area there are a lot of very complicated engineering devices like a drilling platform, and also there is a happen to be they began the active navigation along the Northern Sea route, and if if there will be such kind of explosion near the drilling platform or near the or near the ship, it will be not so good for them. So, and it is the map with distribution of the gas hydrate in the North Sea, in the North Seas of the Russia, and in the shelf, you see that it is a very huge territory. So that means that it will be, it is very, very important, and it will be very actual to have some tools for recover the concentration of the gas hydrate. But unfortunately, when it is in the frozen in the ice form, it is almost the same as the reference medium, and there is no way to distinguish between gas hydrate, methane hydrate, and the surrounding media. And the only hope, I suppose, in our opinion, is that we may follow the attenuation of this area. Because during the melting there will increase the attenuation of the seismic waves in this area, and you may understand that if there is if you will do the monitoring of the elastic properties, and you will see that there is the same parameters like VP, for example, but the increase of the attenuation, like quality factor for P and D. So that means that there is the melting, because that means that the solid phase is going to become the liquid phase, and so it is. It may be some kind of prognostic features to have some action, for example, to close the navigation in this area, or maybe to prepare some the engineering decision for the structures like drilling platform. So the wave propagation velocity for the viscoelastic media, it is almost the same as for the classical elastic media. The only difference is in the Hooke's law. So, just a moment. So that means that the connection between the stress tensor and the displacement tensor and strain tensor is done by the convolution integral with the green function. So there are a lot of different models which are describing this behavior of the viscoelastic media, but we have decided to start with the generalized standard linear solid. It is the model for the Hooke law. It is like presenting here in this slide. There is a mutual derivative with respect to time, mutual time derivative of the stress and strain. And so that means that when we will come to the differential equations, that will be equations like this one, and there appears the so-called attenuation alpha from omega, and the dispersion equation looks like this one. So there is both the phase propagation and attenuation, which are dependent on the time. But it happened to be that for the seismic waves, there is no change of the quality factor with respect to frequency. So that means that you should introduce a few attenuation mechanisms, a few parameters to describe the attenuation. So finally, we have decided to look to deal with this kind of the quality factor, and that means that we should to recover some kind of this kind of relaxation times. So let me move to the equations which we use for description of the wave propagation velocity, of the wave propagation through the elastic media. They looks like this one. You see that here are the two parameters, tau p and tau s. It is the parameters which are responsible for the attenuation, and we will concentrate on the recovery of these parameters. So if we will present if you will fix the so-called reference media, that is Lam parameters lambda mu and the quality factors tau p and tau s, we may synthesize the wave field, which is the function, which is the operator of these parameters, and the inverse problem is resolution of this kind of nonlinear operator equation. Of course, it is a rather difficult problem, and we are not going to deal with the full nonlinear statement. We will suppose that we already know the structure of our medium rather well, that is, we know the reference medium, and we suppose that the reference medium is without of attenuation. Then our acquired data, they depends on the Lam and the quality factors like this kind of linear integral equations. And finally, we come to the linear integral equation, which connects the perturbation of the elastic and the attenuated parameters with and maps them to the input data. So in order to understand what happens in this statement, we have decided to do the numerical experiment with such kind of the model. The most important feature of this model is that perturbation of the parameters are in the different spatial domains. So it is very upper, it is the perturbation of lambda, then perturbation of mu, then perturbation of tau p, and next and finally perturbation of tau s. So we come to the if we will see that, so that means that we need to resolve this kind of linear integral equations with respect to these parameters. We do it in the traditional way, that is, we do the discretization, we come to the matrix linear algebraic equation, and the first thing which was done, the first stage, it was the computation of the SVD for this matrix, and we see that there is very sharp, very sharp decrease of the singular values for when there is a size, when there is.
Sorry, you also have a couple of minutes left.
Okay, so we performed this kind of computations, and we came to the following result. So if we will use the very low condition number, we can recover nothing. So you see that there is almost no information about our distribution. But when we increase the condition number, we come to the more and more clear presentation of the perturbation of these parameters, and we can split this perturbation. So on this computation, we can do the conclusion that straightforward implementation of full waveform inversion in a viscoelastic medium inevitably leads to the coupling of parameters like the quality factors and the wave propagation velocity. To separate this perturbation, it is necessary to perform a singular value decomposition. To understand which singular value is possible, providing us with the desired information, and using the found operator angle, determine the condition number, providing both correct separation and stable solution. So thank you very much for your attention. This study was supported by the Russian Sound Foundation. So my talk is over. Thank you for attention. Questions, comments, I will be happy to answer them.
Right, thank you very much. And so is there any question either from the room or the audience online? Please feel free to unmute yourself. So I guess everything was perfectly clear. So thank you very much again for your presentation, and let's thank also the other speaker of this session. And thank you very much, and we will see you at ICCSA in some other session. So thank you again.
Okay, thank you.
Thank you.
Степа, все.